Hello, in this video of electrical engineering series we're gonna be exploring a magnetically coupled networks of two inductors. In this video, as you can see, we have a bunch of meshes on the left side, and we have two magnetically coupled inductors with minus 1 ohms, or J, because in electrical engineering we use J instead of I as the imaginary number, so we don't get confused between current and the imaginary number I. And the goal of this exercise is to find the voltage at the 2 ohm resistor on the right. So in order to do that, you need to find the current of the mesh on the right, which we call the mesh 4, as you can see here. So in order to do that, you're gonna have four total meshes, and each mesh will have its own current, and by the end you will find the current for mesh 4, which is I4, and multiply by 2, which is the resistance, because you know from Ohm's law voltage equals IR. So if you multiply the current 4 with I with the resistance, which is 2 ohms, it should give you the voltage across the 2 ohm resistor, which is V0. So let's go ahead and start doing the exercise. So as you can see from this, so we consider this mesh number 1. Let me just write it down neatly. So we have mesh number 1 here, mesh number 2 here, mesh number 3 here, mesh number 4 here. So you have 4 total meshes, as I said before. So for this one, we're gonna go clockwise. So we go start at this point here, and we go all the way back to it, clockwise. So some people, the way they do it is when they see like a voltage drop. So if you have like current going through 2 ohm resistor, you have voltage drop. This is doing it by negative sign. But for me, I just use positive sign for it and negative sign for the voltage, for the power source. But in this case, your power source is going to be also positive, because you go from positive sign to negative sign. So it's just a convention. So no matter what your convention is, the most important part to be consistent across all the 4 meshes in the exercise, so you don't run into issues. So first thing is we have I1, so just put I1 here, I1. So it's going through the 2 ohm resistor, and it's going this direction. So the voltage across the 2 ohm resistor is gonna be I1 times the resistance, which is 2, plus across the 4 ohm resistor we're gonna be the same thing, 4 times I2. And now we're going to the 12 ohm resistor. 12 ohm resistor has 2 currents. It's going to have 2 perspective currents. The first current will be the I1, which is in this mesh, minus I2, assuming mesh 2 is in the opposite direction. So you end up with getting 12 times I1 minus I2, and that's equal to minus 12 volts. Or you can just do it this way. Some people do it this way, so they add the volt, so they just like add. So since you're going from positive to negative, it's gonna be plus 12 volts, and you move the voltage to the other side of the equation. That's how you get the minus 12 volts. So you don't put them at 2 sides of the equation, just put them on one side of the equation. But I'm just explaining here how you get the minus 12 volts. So since you're going to the positive terminal, negative terminal, you have plus 12 volts, and you move it to the other side of the equation, you get minus 12 volts. So let me go ahead and erase all these. So that's for mesh 1. Mesh 2, which we're going to do it in different color, let's do it in yellow. We have the current going this direction. Again, we're going clockwise, and in this case it's just an assumption, so you can say counterclockwise, but since we put negative here first, So I assume it's in the opposite direction of I1. So if you can see, if this goes like this way, if it's like moving this way, I1, I2 is moving the other direction. So we got 12 times, again, I2 minus I1, assuming that in each case, in each separate mesh, we assume that the main current is the strongest, or the current with the highest magnitude. There's magnitude and is in the positive direction. So in this case we get I2 minus I1, and the resistance 12. We go plus 4, we have this resistance, times I2, which is still the same current, minus I3, which is the current in the third mesh, and it should be equals to 24. So again, you can do it the other way around, which is what you do is here is, since you're going to the negative terminal of the voltage, you get minus 24 volts, and you move it to the other direction, you get the positive 24 volts. So you just erase all this so we don't get confused. And the last but not least, or the second to the last, we have the, do it with careful I guess, we have the third mesh, and so going this way clockwise, and in this we have two imaginary components, the minus 2i and the ohms and the 4 or J4 ohms, and when you add them you can add them together, that's fine. You can do the same here as well, but because I was showing off the subtraction between, or the difference between the two currents that going into the same component, I was splitting them out. So in this case you can write just 6i1, and here we just add them together. We got, in the third mesh, we get minus 2 plus 4j, that gives you 2j, so that's why we get 2j here, I3. So instead of like writing minus 2j I3 plus j4 I3, we can add them together, so you get j2 I3. And we have also the 4 ohm resistor, the 4 ohm resistor as well, which experience two different currents, I3 and I2, as you can see here. And we assume I3 is in the positive direction and the I2 is in the negative direction with respect to the mesh 3. And we get I3 minus I2, as you can see here. And we have the coupling constant, or the magnetic coupling constant, or inductance I would say, which is minus J1 ohm. And so now we have the dot convention. So as you can see here, so we need to pick other direction for the, so let me just do it really quick here. So just use the blue. So for mesh 4, we assume the direction is going clockwise as well. And in this case, through dot convention, we see this dot, the current is entering the inductor of the transformer, and in the other case, the current, which is I4, is entering the conductor as well, the inductor as well. So we have plus sign for the magnetically coupled constant, or inductance. So in this case, it's negative already. The value is negative 4, it's negative J1. But since we said in this case it's entering the, in both cases, or both separate currents are entering the inductors at the same point, at the same time, not the same point, at the same time. So the mutually, or the coupling constant, will be positive. So that's why you have, so you can write this way, so let me just explain more better here. So we have, so in this case we have this with a plus sign here. So you know plus times negative is just negative. So I'm just make my plus sign better. Sorry, I'm still learning how to write with the stylus. So that's how you do it. And there's no voltage power source or voltage source, so just put 0, equal to 0. That's mesh 3. Mesh 4, we already know the direction, we just pointing out. So it's going to be minus J. So let's forget the coupling, and let's do the J, the imaginary the imaginary component. So you have 3J and minus J. So that up to do 2J I4 plus the resistance 2 I4, and the magnetic excuse me, the magnetically coupling constant will be, in this case, positive again, because they're entering the dot convention. Because of the dot convention, they're entering the inductors at the same time, and that's positive sign here, and so it's equal to 0. So we have 4 meshes now, as you can see. We have 4 unknowns, so it's solvable, but it's going to be really difficult. So in order to avoid doing mistakes, I wrote script, as you can see here. That spelled out the solution for us. As you can see, we care about I4, which is X4 in this case, which is 0.98 plus 0.12 I amperes. And we know the resistance back here is 2 ohm. So we know from Ohm's law, V0 equals I4 times R, or IR. And I in this case 0.98 plus 0.12 I times 2. And that should give you 1.96 plus 0.24 I voltage. Or volt in this case. That's one form of writing the equation, but most teachers will ask you to write in the polar form because it's easier to deal with it, or it does make more sense to do with the phase domain. When you work with the phase domain, to write in the polar version, not the imaginary version or the complex version. So when you write in the polar form, you get 1.97 with the angle almost 7 degrees, 6.98 degrees volts. So that's how we do this problem. So they see the hardest part of this problem actually is just solving these 4 simultaneous equations. But by setting up the equations are pretty easy. Just like follow the path of the current. So please, if you have problems with solving this 4 simultaneous equations or getting these numbers, let me know in the comments below, and I'll be happy to provide you the scripts or codes, or I have programs. A program that it just runs on Windows. I can like solve the up to 5 equations, simultaneous equations, for you. You just enter how many equations first you need to solve just to set up like the parameters, and then you enter the real and imaginary part. So that's it for this video, and see you in our next videos.